So, welcome to my third and final installment in my series of talks about the singular Yamaha flow. This talk is about the convergence of the flow and lack thereof. So, we already established the existence of the flow and for an arbitrary time interval. And now I want to show what happens as time goes to infinity. The first thing you need to get are some time-independent estimates. Previously, I just shown you time-dependent estimates, saying if you flow for up to a finite time big T, then you can get bounds, but that bound depends on big T. So you need something which doesn't depend on the finite time. And you can do the same argument in our setting, in our singular setting, as Schwedlik-Struve first did, and then Brendel. So our arguments are more of a mixture of both of them. And what you can show is that for any p between 1 and slightly bigger than n/2, n/2 is a sort of magical exponent for the scalar curvature. The scalar curvature converges to the average scalar curvature in LP norm. So there's a caveat here. This is the LP norm with the time evolving metric. So there's a slight problem with that, but at least that's what you get. So this is sort of what you want. You want the scalar curvature to be constant. So the scalar curvature converging to a constant is good. So from this thing, you immediately get that the scalar curvature is uniformly bounded in LQ norm, at least. This is also good because this is sort of the setting we want to be working in. I won't give you a complete proof of this thing, but I'll give you some of the proof because it sort of tells you how you work in this setting. So the key ingredients are, I already wrote down the Yamaha flow equation, so what the solution looks like what the conformal factor evolves like. So if the conformal factor evolves, you can also write down how the scalar curvature directly evolves, and the equation is kind of nice. It's this one. It's tempting to call it a linear parabolic equation. It's not quite true, because this thing, this object, is the Laplacian of the time evolving metric. So there's a time dependence hidden in this Laplacian. But otherwise, it's a very nice equation. And the volume form, you can also quickly compute how it looks. So it's essentially like the Yamaha flow itself, but with a different constant here. And those are the two equations we will be using to prove at least parts of this. At least give you a flavor how you prove that. So let's start. So you have this average scalar curvature, sigma. This is just the integral of the scalar curvature. You can compute the time derivative of that. So you get two terms, time derivative of this plus the time derivative of this and this. And then using these two equations and the fact that compactly supported functions are dense in H1, so I don't have any boundary terms, I can just remove the integral of this Laplacian. This Laplacian just integrates to 0. I don't have boundary terms. So using that, these two equations, you immediately get that the total scalar curvature evolves like this. Now, a short trick, because the integral of this thing is 0, so you can sort of subtract sigma times this, or the integral of that. That's just 0. So this thing is actually this. And what you see from this is that the total scalar curvature is decreasing. If you just start with the Yamaha flow equation, just taken out of the blue, this is a miracle. Hamilton sort of designed it like this because he was looking at a negative gradient flow of the total scalar curvature. So if you're looking at a negative gradient flow, then the total scalar curvature should go down. It's how you design this thing. You designed a flow so that the energy, this thing, goes down. And that's what happens. And this is extremely important. It's important in geometric flows generally if you have some kind of monotonicity going on. It says the total scalar curvature is decreasing. Great. So I already told you when I discussed the Yamaha constant that this is a lower bound for the total scalar curvature. So you have a monotonally decreasing bounded from below function. So by calculus, this converges. So the total scalar curvature converges. No additional assumptions yet. That's nice. That's good, at least. So what can we do with this? And here comes the trick. So you can then write the scalar curvature at time t, the total scalar curvature at time t minus the initial one. You can just integrate the derivative, of course. But we know what the derivative looks like. This was the derivative. So naively, it's not true, but naively you would then think, well, this thing converges, and this integral has to converge. Hence, and this is the false bit, the integrand has to go to 0, because this integral then goes to infinity. That's not quite true. It's almost true. What's true is that the lim inf goes to 0. So the fact that this integral converges tells you that the lim inf of this integrand goes to 0. Okay, but that's at least something. So we want to show that this thing goes to 0. At least now we know that the lim inf goes to 0. How do we deal with the lim sup? Well, we got this far, but just differentiating the integral of the scalar curvature. So we might think, well, if I differentiate the integral of the square root of the scalar curvature, or more precisely s minus sigma, I might get something. And that actually turns out to be the case. So you just compute this thing. Use the same equations as before, just slight difference. I can no longer discard the Laplacian, but I can integrate by parts and get a gradient term, which I then will discard for this argument. But for later arguments, we want to keep it. But then I can discard this. And after some algebra, you just get this. And let me just cheat a bit. So the statement, the theorem is true for dimension 3 as well. But you see, when you do the algebra, you get this term popping out. So n equal 4 is super easy because then it just vanishes. And at least 4, you get a good sign on this term, so it's negative. For n equal 3, this thing has a bad sign, and n equal 3 is a bit annoying, but things work for n equal 3 as well, but I won't tell you why. So from this equation, you get a little differential estimate on how this L2 norm evolves with time. And that you can use. You can take this equation, or inequality rather, and integrate it from, say, s to t, where s is smaller than t. And that just gives you this thing. Okay, so far so good. So the reason why this is good because I can say something about this integral. So you can then say, well, if I set s equal to t minus 1, so just do a unit step, then this thing is still the same. This thing is this integral, and then you can estimate this thing a bit and get that the whole thing you can just estimate from above as this integral. Now this is the same integral we had for the average scalar curvature. It's up here. Except I don't integrate from 0 to infinity, I integrate from essentially t to infinity. It's a small trick. And then I can say, well, if I then send t to infinity, then surely this guy goes to 0. Hence, the lim sup of this thing goes to 0. So it's all this argument boils down to monotonicity of the average scalar curvature allows you to get your foot in the door and have some kind of convergence somewhere. And then you play around with the evolution equation. And this is it's a bit fun, but it is also a bit tedious technical to do these computations. And the computations are really sensitive to all the different coefficients you have lying around. So for instance, the sign of this term. But that's essentially all you're doing. You just have to be a bit focused when you do this. Okay, so this is just L2, but I promised the LP for t smaller than half the dimension plus 1. But the other arguments are similar in spirit, but more technical, so not something you put on a slide. So let's just assume now we've proven that Schwittlich-Struve-Brendel result. So we then know that the scalar curvature converges the average scalar curvature in LP now. So what about the conformal factor? So the conformal factor also has to converge. That's sort of the solution. Well, that's a more complicated story. So this is a long statement, but let me try to parse it. So it says if you take some sequence going to infinity, and then of course makes appropriate names for these, the solution at time tk and so on, then you can pass to a subsequence so that you converges in a sense to something solving the Amabe equation, so the equation you want for a constant scalar curvature metric. But what do I mean by converges? So there are two cases which can happen, and only two. So it's a dichotomy. Case one, the good case. The sequence or subsequence converges strongly in H1. This is a good space, first order space, and even in Hölder norm. So it's in particular continuous. It converges pointwise to this solution. So this is the thing you want to happen. What can happen and will happen in the example at the very end is that you get weak convergence in H1 of UK to this solution, and at finitely many points something goes wrong. So if you take away finitely many points, then on compact complements of those points, you can bound your solutions up to the second derivative even, and you have convergence locally away from these problematic points. Here's a caveat. I don't say anywhere in the statement that U infinity is positive. U infinity might be 0. And that will happen in the example. So if U infinity is 0, I don't really have a solution to a constant scalar curvature problem because I just have a 0 conformal factor, and that's not allowed. I need a positive function. But that's the state of the art. So there's a similar dichotomy in Schwittlich-Struve for the smooth case, and the spirit of the argument is similar, but with some modifications. Okay, so let me give you an idea how to get this started. I won't give you the full proof, but at least sort of a rough idea of how do you even start on this. And forgot there's also a bound. We don't really need it, but I said there are finite and many problematic points, and you can actually bound this number. It's given like this. At least an upper bound is given like this. Okay, so when you see weakly convergent sequences in H1, you sort of expect Banach-Arloglu. I'm going to show that the sequence is bounded, hence there's a weakly convergent subsequence. So I need to show that this function U is bounded in H1 uniform. Well, we had in talk 1 that you can express the scalar curvature S of the conformally changed metric like this. So if you just multiply by U and integrate, you get this equation, or inequality rather. So it's an inequality because I used a Hölder inequality here for this product, for the product with the integral of this product. So what does this tell us? Well, this is the thing we want to bound. This, if you look carefully at the definitions, is the volume, and that's normalized to 1. And this thing, well, we know that S is bounded in LQ, and we have finite volumes. So if it's bounded in LQ for Q bigger than 1, then it's bounded in L1 as well, this thing is bounded. And this is just a constant. So the gradient of U is uniformly bounded in time. Okay. The L2 norm of U is of course bounded because this thing is bounded uniformly. And this exponent is bigger than 2. Might not be obvious, but it is. So you get uniform bounds on the H1 norm of U. And then Banach-Alaoglu tells you that bounded sequences have weakly convergent subsequences. And this H1 is a Hilbert space, you can identify it with its dual, so you get weakly convergent subsequences. The Banach-Alaoglu, strictly speaking, says you have boundary weakly convergent sequences in a dual space. And so that sort of tells you how you get subsequences. It's just a boundedness argument and a completeness argument. Right. So for the volume forms, you do something similar. Essentially just saying this thing is bounded, hence has some weak star convergent subsequence. And same for this thing, which you can sort of think of as a volume, or at least as a measure. And that sort of gets you going. But I promised you more. I didn't just say, well, you have weakly convergent subsequences. I said you should have Hölder convergence as well in some cases, either local or global. So to get that, I'm going to have to talk about a Harnack estimate. But before I can talk about a Harnack estimate, I need some more local constants. So I talked about the local Yamabe constant, and here's a cousin, namely the local Sobolev constant. So it's just defined as the infimum of the gradient of a function, so of all functions, subject to the constraint that the volume is. So it's sort of obvious that this is sort of thing you want to consider in this Yamabe setting. This is sort of the things which appear, but that this is a good thing is that this actually leads to something is less clear if you haven't done it before. And exactly like for the Yamabe, local Yamabe constant, we define a local Sobolev constant by taking a limit of r equals to 0 of such balls, and then the infimum over all points. So in certain cases, this thing actually equals the local Yamabe constant. So certain cases means our setting, because we can show that the scalar curvature is uniformly bounded by is uniformly in LP for P at least n half. So what can you do then? Well, the Harnack inequality we need was already established by Akadogawa-Cohen and Matsuo, which says that if you have a function with two weak derivatives in LP, and a conformal metric, as we've considered all along, and you have a volume normalization, and you assume that the scalar curvature is uniformly in LP for P at least at n half, then the statement is, so this is just a setting, the statement is, if the scalar curvature doesn't accumulate. More precisely, if the integral of the scalar curvature over a ball, the positive part if you want, is smaller, strictly smaller than the local Sobolev constant of that ball, and the strictly smaller has to be uniform, then the function is actually bounded from above and below, and its Laplacian is bounded from above and below in LP norm. Strictly speaking, on slightly smaller balls, but that's sort of usual for the Harnack inequality. That it's 1/8 here, it doesn't really play a role, it just has to be some smaller ball. But that's sort of what you possibly know from Harnack inequalities, that you have to shrink the ball a bit you're looking at. I won't get into the proof of this. It's a bit technical, but it's also not terrible. It's doable, but it's a bit technical. So this we can combine with a small energy bound or assumption. So I'm saying it's due to Aldana, Caron, and Tapi. They have a very similar argument, at least, but small energy leading to convergence is also contained in the work of Schwettlich and Struve. So we just built on their arguments, essentially. So the statement is, if you assume your initial scalar curvature in half norm is strictly smaller than the local Yamabe constant, then you always land in case 1 of the dichotomy, meaning you have convergent subsequences to a solution of the Yamabe problem, and convergence is even in a Hölder space. So you solve the Yamabe problem. So let me just sketch a proof of that quickly. So I said, in our case, so because the scalar curvature is uniformly in LQ, you can show that the local Yamabe constant is equal to the local Sobolev constant. And then it's just a chain of inequalities, and this is where you see that this argument is actually a bit coarse, but we don't have any better ideas. So directly from the evolution equations, I didn't show you this, but it follows in the same spirit. You can show that the n-half norm of the scalar curvature is non-increasing. The other norms might change, but the n-half norm is not. It sort of has to do with the n-half norm being conformally invariant. So the scalar curvature at time t is in n-half norm is bounded by the initial scalar curvature. And this you assume is smaller than the local Yamabe constant, so this is equal to the Sobolev constant. And this is sort of what you needed for the Hanake estimate. You needed that the scalar curvature was smaller than the Sobolev thing. And here is where the argument is a bit coarse. Then we just say that the scalar curvature in any ball is smaller than equal to the total scalar curvature. So you sort of estimate your local scalar curvature by the global one, which we don't have any better ideas, but it's sort of unsatisfactory. Right, and that immediately allows you to use the Hanake inequality, so your solution is bounded, and then you land in case 1 of the dichotomy. Right, so let me quickly say what can go wrong. So this is example due to Jeff Wiaklowski. We worked out some more details of it, but the idea and the first argument for this is due to Wiaklowski. So you just look at a very nice space, namely the Iguchi-Hansen space. So if you're interested, it's globally the cotangent bundle of CP1 or the blow up of C2 mod plus minus 1 at the origin. You can also just think of it as C2 without the origin. It won't really matter today. This is your smooth manifold. To this, you add a point at infinity. So this will then be an orbifold singularity at infinity, but let me say a bit more what I mean by this. So the metric you put on Iguchi-Hansen space, why it's famous, is you can put a Ritchie-Flat metric on it, which is asymptotically Euclidean. If you want, it's given like this in local coordinates. But you don't really have to look at this expression too much. A is just a constant. It's the size of CP1, but it doesn't matter. It's just a positive constant. You take this metric and then you rescale it by this factor. But you rescale it with some factor which goes to 0 at infinity and goes to 0 faster than the metric itself. So you sort of bring infinity down to a finite distance. In doing so, you kill the metric at infinity. The metric degenerates to 0 at infinity. So it's a singular metric at infinity. But otherwise, it's a smooth metric. And it's singular just because it goes to 0 in a very controlled fashion. So in this case, one can show that the Yamabe constant of this metric is equal to the local one. some work to show that, but it's true. So using this metric, it's explicitly given, so you can compute the scalar curvature. I'm not going to ask you to do so. I've done so for you, and it's this. So it's a bounded function. It's of course then also an LP for p bigger than half, and so on. And you can also see that this m bar I introduced here with this metric is a compact metric space. So it satisfies all of our conditions you can check. So what happens? So I'm claiming the Amaba flow does not converge on this space. So since everything is explicit, we just thought we'd have a look at how things look, because you can write everything explicitly. So this metric has some rotational symmetry going on. So the solution is also going to inherit this rotational symmetry. So the Amaba flow is just going to have a radial component and a time component, but no angular components. And you can explicitly write down the entire Yamaha flow, and it's just this equation. Sigma tilde is essentially just the total scalar curvature, and V is the function you want to solve for. This is the PDE you have to solve. So it's non-linear, but it's super explicit. So we can't solve it explicitly, we're not that good, but we just, for funsies, did some numerics on it. Just sort of short time solutions. So the black line here is the initial state. You start off with conformally rescaling by 1, so you don't do anything. And as time goes on, so let me point out, with this relabeling X, I've done the standard trick in single analysis that you put infinity at 0. Might be a bit confusing, but infinity is down here. So you see when R is infinity, this is 0. So for short time, for small time, you don't do really that much conformal rescaling, but you sort of you see you accumulate more and more mass at infinity. And after a short time step, you sort of see a trend here. The mass is accumulating at infinity, and we can show that what happens in this case is that the entire mass concentrates at infinity. So the function u infinity in this case, the u infinity of the dichotomy, is 0. So it solves the Amaba problem. Kind of, it solves the equation, but it's a 0 solution. And your subsequence will converge to 0 away from this special point. You have one problematic point, that is infinity. And at infinity, the solution just blows up. All the mass goes into infinity. So it's kind of like a Dirac delta here at infinity. This is sort of what can go wrong in a singlicity. Just a small outlook. Something I didn't talk about because I didn't have time. I didn't take the time. So I just showed you what can happen. I just said at a single point, for instance, all the mass can go into this single point. One might be then interested in asking, well, can you give me a more local description? So, okay, mass concentrates at the point, but if I sort of Gromov-Hausdorff rescale that point, can you then say something about what the solution looks like and on a different scale, so to speak? And yes, we can. That's in an appendix, at least for settings like the Iguchi-Hansen space, or more generally for stratified spaces. We have a bubble description. So you have bubbles appearing. So after rescaling, you get solutions which look like the classical bubbles, where you can at least pick subsequences, you get that. But I won't talk about that here, but that's a long appendix if you're interested in that. So the big open problem is Akutagawa, Caron, and Matseo showed that the elliptic solution always has a solution when you have this inequalities satisfied. We don't know if that's the case for the parabolic problem. Does the Yamaha flow always converge if this is the case? We don't know. I kind of suspect it, but I don't know. But you saw already in talk 1, the smooth situation already for the Yamamoto law is more complicated. Even for a smooth compact manifold, it's kind of hard to talk about the convergence. And there are obstructions there. So that sort of, we don't really know. And it boils down to understanding what this local Yamamoto thing says and how rigid single manifolds are. Right. So like for the other talks, there's some further reading. If you want to look at the bubble formation, this is the paper I've been talking about for 3 talks. It's on the archive. And otherwise, you can look at all these other papers having to do with the Yamamoto. So thank you for your attention and have a nice day.